Hello, this is a short guide to building your testing method on the Mastersizer 3000. Wet and dry analysis is possible on the Mastersizer 3000, depending on the accessories you have in the lab. Liquid and powder samples can be tested wet by dispersion into a suitable liquid. Dry analysis can only be done on dry materials. So let's start discussing wet dispersion analysis with the Mastersizer 3000 and its associated wet accessories. We will start by first concentrating on the sample preparation and measurement steps. These depend on the sample type. Is it a suspension, an emulsion, or a powder? Always build your methods in manual mode so that you can learn as much as possible about your sample before locking in the method. Here are the steps needed for a suspension. Fill in the accessory tank with water, solvent, or oil, depending on the suspension carrier. Mix the suspension well to resuspend any settled material, and then, using a pipette, sample from the middle and add the sample to the accessory tank. Make sure that the pipette is wide enough to accommodate the larger particulates in your suspension. The obscuration limits for wet measurements are 0.5 to 20%, and the light energy should ideally be above 10 scattering counts at peak. Then take consecutive measurements of the sample while checking the obscuration and key size parameter trends. This can be done directly in the measurement window. You want to have the sample in a stable dispersion state when you measure it, otherwise your measurements are going to have poor repeatability and reproducibility. To test for stability, take measurements before, during, and after sonication, what we call the B-DAS methodology, and observe the trend in key size parameter. Never average on changing data. For an emulsion, you can apply the same steps as for a suspension, except the stir rate must be kept low, 1800 to about 2000 rpm, to avoid changing the emulsion while you are measuring it. Gently mix the emulsion and sample from the middle. The obscuration limits and light energy peak are the same as for suspensions. Then take 10 or 20 short consecutive measurements and observe the obscuration and key size parameter trends. Don't sonicate emulsions as the droplets are likely to burst. If poor stability is observed, that means that the emulsion is changing due to the dispersion liquid. It is best to measure it in the mother liquor, which can be obtained by centrifugation or recreated based on the original emulsion recipe. For example, in an oil and water emulsion, the mother liquor is everything in the emulsion but the oil. For a powder measured wet, first fill accessory with water or a suitable liquid. Then make sure that the powder wets well in the liquid in which you add it. I included two pictures here that show poor and good wetting. If the powder runs away from the liquid or makes a layer on top of it, that means wetting is poor. Adding several drops of a dilute surfactant solution typically helps improve wetting, as shown in the figure on the right. Make a thick consistency paste of the powder in liquid and add it dropwise to the accessory. This improves sampling of the various size particulates in the sample. For a high-density powder, sedimentation in the beaker or pipette might cause poor sampling. In this case, you will need to add the full sampled volume to the accessory tank. Same limits and for obscuration and suggestions for light energy apply. You can then treat a powder exactly like a suspension. Take consecutive measurements, look at trends, do a B-DAS study, and only average on stable data. The best predictor of success for size testing is the stability of the results, so it is important to observe trends in real time. Let's first look at obscuration changes. When you see the obscuration rapidly dropping to zero, that means the sample is soluble. you need to change the liquid in the tank. If the obscuration is decreasing, the sample might be sedimenting and you need to stir faster, or the sample is agglomerating. You need to stabilize it. Use a dilute solution of sodium hexametaphosphate or sodium pyrophosphate. When the obscuration is increasing before applying sonication, the sample is dispersing due to the energy given by pumping and stirring. You can either wait to reach stability or speed up the process by applying sonication. The ideal case is stable obscuration, of course. The changes in D90 also tell you a story. A sudden drop to zero, the sample is soluble. If it decreases, the agglomerates are dispersing. Either wait or apply sonication to reach stability. If the D90 increases after turning the sonication off, your sample is agglomerated. Add a stabilizer. Ideally, of course, you want to see that the repeatability in D90 is good, and that denotes a stable dispersion. Once stability is reached, you need to check precision. This is typically done using repeatability and reproducibility studies. Let's start with repeatability. Once the dispersion is stabilized, the only factor that influences repeatability is measurement duration. This needs to be long enough to make sure that the largest particles have time to circulate to the flow cell and be seen by the laser. Here is an example repeatability analysis for a sample measured for 15 consecutive measurements. The first 5 measurements are 2 seconds long each. The next 5 measurements are 5 seconds long each, and the last 5 measurements are 10 seconds long each. While D10 and D50 are stable overall, the best stability in D90 is obtained for measurements which are 10 seconds long each. So, measurement duration influences the relative standard deviation on key size parameters, and D90 is the most sensitive parameter to measurement duration. Mathematical calculation of repeatability shows that the RSD for D90 is best when the measurement duration is 10 seconds. This is also confirmed by looking at an overplot for the 5 consecutive measurements of the sample when stability is reached, and for 10 seconds long measurements, thickness of line overlap is obtained. To recap, to improve repeatability, you need to consider the top end size, which will influence the measurement duration, the material density, which will influence the choice of stir rate, and the dispersion state. If the material wets poorly or it aggregates, you need to add surfactants or stabilizers or sometimes both to improve stability. Another consideration is reproducibility. How stable are the results if you use the same method on different aliquots of the same sample? Once the method has been optimized for stability and good repeatability is obtained, the only parameter that can influence reproducibility is sampling. Are you taking a representative sample from the original one? Check Dr. Rawls' papers and webinars on sampling to understand the concepts and improve your sampling. Here is an example of great reproducibility for 3 different aliquots of the same sample. This is also shown in the frequency plots obtained for the tree analysis. Great overlap is obtained here. Remember, once the sizing method is robust and stable, the only influencer for the reproducibility is sampling. Make sure that is done appropriately. More details in the webinar linked here. Let's continue with dry dispersion analysis with the Massesizer 3000. Do not forget, only dry materials can be tested using dry dispersion analysis. If the material is slightly wet, you will need to measure it wet dispersed. First, make sure to mix the original powder well. Then, depending on the sample volume you have and the top and size of the powder, choose your sample tray. The general tray with hopper, shown here, is the most common one. I would use the micro tray for small amounts of fine powder and the funnel feeder when a whole bag of sample needs to be measured. Then choose your venturi. The standard venturi is used for most samples. The high energy venturi is only used for fine cohesive materials. The obscuration limits are 0.5 to 6% for most materials. Limit the upper obscuration to 4% if very fine material is tested. Because dry flow is not always perfect, it is best to limit analysis to the obscuration limits. Continue by adjusting the flow rate and hopper height such that the scattering falls nicely within the limits and take consecutive measurements. Short consecutive measurements help you understand the sample homogeneity and any segregation on the sample tray. Longer measurements help you decide what sampling is needed for good reproducibility of the results. The air pressure chosen for analysis might affect the powder dispersion. Some materials will be so cohesive that a high pressure is necessary, while others might be broken if too high pressure is applied. When developing the method, it is best to build a pressure-size titration curve and understand its effect on the results. For best sizing, compare results with a wet, well-dispersed result to fix the pressure. If you want to look at bulk properties for a powder, use low pressure of analysis. Here are two examples of a pressure-size titration curve. These are the key size parameters obtained for a material when tested at different air pressures. Ideally, pressure does not affect the result. This might happen for materials such as metal powders. Typically, however, some changes are observed. If the material is friable or very cohesive, the results will depend significantly on the pressure used. If you observe changes with the air pressure applied, then use low pressure if the bulk properties of the powder are needed. Use the pressure of best overlap with a wet measurement when interested in the size of the dispersed material. If only relative results are needed, choose any pressure of analysis, but keep it consistent across time and different batches of the same sample. Examples of good and decent dry-wet overlap results are shown here. We have perfect overlap on the left and decent overlap on the right. Small differences in the results are obtained, but the key size parameters are quite close. These are examples of poor overlap. Dry analysis disperses the material to smaller sizes in both cases. You have to consider lowering the pressure. For the right-hand case, though, this will leave large-size material poorly dispersed. Typically, dry size curves are broader than wet sizing curves. Some attrition and some poor dispersion is typically observed dry. For some materials, however, dry offers the advantage of easy analysis without the use of expensive solvents or oils. Repeatability studies are not possible for dry analysis. A different aliquot is measured and sent to the vacuum at each time. You cannot measure the same sample unless you somehow recover it from the vacuum or at the end of the dry flow cell. In terms of reproducibility, the influencing factors are the method, the flow, and sampling. You want the same method with a constant flow and appropriate sampling in terms of volume and measurement duration. Here is an example of a reproducibility study for a sample that is homogeneous enough that 2-second long measurements are enough for great reproducibility. This sample is so inhomogeneous in size, however, that the variability is large even after 15 seconds long measurements. In this case, measuring a larger volume of sample with a funnel feeder might be of use, or simply accept a larger variability in the results. In conclusion, spend the time to build a robust method in both wet and dry dispersion, and your sizing results will be repeatable, reproducible, and reliable.